This is advertised as a workshop on the design and implementation of Modtalk. However, scratch that out. This is really about the implementation and design of Modtalk, because that's how it really worked. We really didn't have a clear idea of what we were doing for large parts of the project, and we took a tactical approach. We spiked in implementation and got one slice of it working end to end, and once we had that, we could take a step back and say, this should really be separated here, and you get out the code chainsaw, and some people call it refactoring. This is more like code chainsaw time. Yep.
Sí.
Mike?
Micrófono. ¿Y ya está todo prendido? ¿Está todo bien?
Yeah. Hello. Hello.
Can you grade?
I don't see a red.
Is it all on?
Well, is the red is on the middle, but that should be off. Let me get what's left of my broken glasses. That should be off. That should be mute, and that should be on. Am I on now? Start the sketch over. Can I do that? Oh, yes. Not the design and implementation of Modtalk. Oh, no. It's the implementation and design of Modtalk. So there's enough complexity in this project that we just did not have a clear picture in our heads of what the design of the implementation should be. So over the last year, I think it's been an opportunity for these four to really experience what it's to be like on a small, highly productive team, which means you're not going to be slavishly devoted to agile practices. You're not going to be writing tests for everything all the time. These are all good things. We value these things, but that's just not reality when you really need to get things done in a hurry. So what we did is we would choose a slice of technology we could get implemented, and we'd do a sprint to get that spike done, and we'd write tests to help test that into existence. Those tended to be very brittle tests. A lot of them we had to throw out. A lot of them we had to rewrite. And that's just a normal part of development. It doesn't mean we wrote the tests wrong. It doesn't mean tests should live forever. We use them to get code working, and once the code is working, we have a better understanding what should be a public interface that lasts, and those are the tests we should focus on. And things that were just artifacts of, this is our idea right now of how it should work, that were too brittle, those tests should go. Okay? So it was a process of experimentation. So what's happened is our experimentation has so far led us to this picture of what's going on. Repository was one of the first things we had. We had to have a place to store our source code modules and pull them back. So that's a very clean repository. That's been fairly stable to the level we've used it. What I'm hoping you can break out, I was thinking we might have multiple groups breaking up, but I don't think we have enough people. One of the things we need to do is really design at a fairly high level, what does it mean to wrap a Git or an SVN repository, and how do we really want to manage that abstraction of, I have a working copy of a repository of a given branch and revision, and how do I associate that back to the source repository? But essentially, the responsibilities we have in the repository to manage versioned objects. So in the repository framework, every kind of object has a type. Every kind of module has a type. Every type of module has its own file extension. And registered with the repository framework is, for every module type, there's a corresponding module reader and writer. Actually, entity reader and writer. You can use the repository framework to revision any object as long as it's a registered type with a reader and a writer class. So anything you can serialize, you can store as a revisioned object with this framework and then use a specification to get it and retrieve it. Semantic was the next thing we had working. So at STIC last year in June, we basically had these two boxes and a horrible hack that took us from our semantic model into running code. In semantic, which Josh Fridstrom will be talking about, it has the basic job of taking a program specification, loading in all the dependent modules, doing the code analysis, making sure the code is correct, compiling the code right up to intermediate representation and no further, And if there are errors, recording where the errors are in the code so that when someone fixes them, that part of the program can be reanalyzed and rebuilt. And when all the errors are gone, it's available for building. Kurt, I don't know, you're probably not going to talk about Builder today.
I was going to talk about exceptions, that process.
Okay, maybe in the second half you can talk about Builder off the cuff. Okay, so Builder is the part that takes a fully analyzed and semantically dressed semantic model and generates the code and generates the object. So while we don't have an image, that doesn't mean we don't need an object graph that represents the program. It's just that it gets compiled into a file segment of the executable. So the way this whole subsystem came into being was we took the part that was just going straight to C code and we started cutting it up into pieces. And in the process of doing that, we recognized there's two distinct kinds of objects we're writing. We're writing out our threaded code as the actual implementations of the method. For example, Javier was talking about how in B kernel you have a compiled method. It has an external address. That external address has a pointer to code. Similarly, we have a compiled method. It has an external address, and it has a pointer to code. And it's writing out those code pieces that our code writers are responsible for. And then the target builder's responsible for managing the cross-references because, as you said, the code needs to point back into the image needs to point at the code. So the ultimate job of the target builder is to manage those linkage references between the code and the object graph so that we can realize them at runtime. And what else? Evaluation. A curious thing, when Kurt implemented our process and semaphore support a couple weeks ago. But to do it, debugging right now is not a fun task. Unless you're really good at GDB and LLDB. And particularly the threaded code, because every step of the interpreter looks like any other step of the interpreter.
And it's like 10 next.
Yeah, 10 next to get through the first step of instruction of a prologue. Yeah.
You have to really know the structure of our...
And you really have to know the structure of the code and the objects. Yeah. So what he did was he actually implemented a bytecode interpreter in Smalltalk and wrote a binary object writer that wrote out a byte array of 64-bit big endian code and had his little interpreter interpreting that binary, which ran slower, but it was faithful and consistent, and that's where we really started getting the idea of how this thing should be designed, that there should be the one target builder and then these pluggable code readers and object writers. We may have left the impression yesterday that this was all done and complete. Well, yes, there are pluggable readers and writers, except there's two different target builders. We have some refactoring to consolidate, collapse, file off the rough edges. So there's quite a bit of refinement there, and we'll want to show you that and sort of go over, the discoveries we made as we discovered what might have been obvious to some but wasn't to us until we actually had an experimental spike working. In the process of doing that, though, when he had his Smalltalk interpreter going, it became clear that this interpreter object that can run one of our compiled programs is itself an ideal representation of what our debug interface should be. It is the abstraction of our execution interface. So we've had these recurring situations where we'll hack something together as part of our experimental spike to get a piece of the system working, and in doing so, further structure of the system will reveal itself to us, suggesting new refactorings and new ways we can make the code cleaner, more reconfigurable, more understandable. And, as an instructor, my goal's been to let these guys know that's standard practice. You're not going to see all the design ideas up front, but design and write your code in a way where you're not afraid to go in and clean it up when you do understand what the design should be. Okay, so that said, I think...
John,
Yes?
before you switch to the slide, is there any meaning to the direction of the arrows?
Yes. So the direction of the arrows is a dependency. So if you read Rebecca's first book, this would be what you would call a subsystem diagram with contracts. So we're saying the IDE, which includes the project and the tools, has a dependency upon the repository's ability to manage versioned objects. Likewise, IDE depends on semantic to analyze, annotate, and load programs and their dependent modules. Semantic depends on IDE to manage repository and build target configurations. Builder depends on semantic and IDE, and it also has a code writing responsibility and an object writing responsibility, and those are distinct contracts for service. So when Rebecca and Brian wrote the first book, one of the early phases of design is these are sort of like, they're not objects, they're nevertheless a high-order architectural structure to the system. And as a design evolves, very often you may wish to have a facade object, which is the front end to this, and these rough contracts for service become well-defined protocols and interfaces. As it is, we have a repository interface. We have a program interface, which is roughly our interface to the semantic component. We're certainly going to want to define a protocol for an interface to evaluation, because one of our goals when Alan was talking about being able to bring liveness into one of these systems, our goal is we want to do the same thing. We want to be able to live edit one of the programs we've compiled, and if Josh does his work right, not only will we be able to debug and inspect and use workspace on that program running over there, but we'll be able to do it on our own process. So when I want to work on Modtalk, I should be able to work on the running Modtalk, should I choose. That's a goal, and nothing that we have working yet. Okay? Other questions about it? Yep, so those are dependencies. The dotted lines mean on number 8, which is provide evaluation control, means we don't have anything there yet. So for everything that's heading toward evaluation, those are really just sort of raw edges where we're leaving Pharo and we're just leaving code artifacts in a build directory. But all of that can be refined later when we get a better idea of what those interfaces should be. And I think at this point I'm handing it over to, Josh. Okay.
Hello, hello. Hello, hello, hello. Oh, I don't need this. Well,
Do you want it?
I mean, not if it's going to take a long time.
We all continue once the presentation is going on.
Okay.
So Josh, why don't you give an introduction?
Hi, I'm Josh. I'm the semantic model guy. So I'm responsible for taking a group of specifications and loading them into a program. I'm responsible for maintaining the internal representation of the program. It's the first level of compilation of a program. So I'm going to be talking a little bit about sort of how the program loader has evolved and sort of the first stab at what the loader looked like, and then some discoveries that we made after we had something working that was sort of the bare minimum that we needed to get a program to compile, and then how those discoveries led to refactoring that has let us reach some of our goals that we have as far as the ability to handle certain cases like errors. Like how do you handle, like what happens when there's an error that affects other things and I can't load this definition and that causes all these other kind of errors, and when I fix it, when I add a definition that is suddenly going to make this method compile now, how do I make sure that everything gets updated and the whole system is intact? So, well, we can skip the first couple slides. So I imported all my slides from the earlier talk just so if we had any questions about how the loader actually, or like what the actual responsibility of the loader is, I can talk about that a little bit more. But to give sort of like an overview, this is a relatively simple representation of what a Modtalk program might look like. You have one program module, two subsystems, sort of importing from each other. This is, it's a very simple diagram, but this is what we have to maintain. this is what a loaded, decorated module looks like. We have all of our program has all of its subsystems, and the subsystems have all of these different types of build artifacts, and it's even more complicated than that because these scopes are like, there's more than one of these scopes, there's more than one of these scopes, and that's kind of a lot to handle, and this is a relatively simple program. So if we add even more subsystems, add even more complexity, then this graph is just going to grow. So that's a lot of objects to structure. So I needed some sort of way to, I needed a structure basically, if we're going to use the stereotypes. I needed some way to build and maintain this complicated semantic model. So we came up with the module manager is responsible for maintaining the semantic model of our program. And the first, one of the things that we quickly realized is, since the elements of a program are all defined by definitions, we immediately realized that managing definitions is one of the key components of our semantic model. So not only are we, if we go back to this slide, not only do we maintain all of the structure of the big picture modules, the program and the subsystems, but all these other build artifacts are all dependent on what kind of definitions there are. So we needed some way of managing that sort of lower level definition. So there's like, so we wanted to be able to handle things like, what happens when you switch to a different branch in your repository? Well, a module might be the same. You might have the same subsystem name, but the subsystem might then have different definitions. So you have to figure out what kind of definitions do I have to add, what kind of definitions do I have to remove. So we have another sort of object that collaborates with our module manager that we call our definition manager. So this is sort of the first very simple diagram describing the first attempt at our loader. And it involves the module manager, which from somewhere over here, we're saying I want our module manager to load our project. So the responsibility that our module manager gives is to structure the semantic model of the program. And then our module manager depends on our definition manager, which manages the individual changes to the definitions. So it's a fairly simple, easy to understand process. So what kind of interface does our module manager need? Well, our module manager, we need to be able to load a program. So that's one thing. We need to be able to load a program from a specification. If you remember yesterday, I talked about the different steps of building the semantic model. And for a program, it involves these four things, basically. Loading the program specification, analyzing the subsystems for errors, making sure there are no cyclic imports, loading the subsystem specifications, and resolving imports for the program. So these are the four methods that need to be in our module manager's interface. And additionally, we need all of these types of behaviors to manage how subsystems are being loaded. Similarly, we need to be able to load a subsystem specification. We need to be able to resolve imports for a specification. We need to be able to add different types of definitions to our subsystem, and including methods. So right now, it's not too bad. I mean, basically, for every step along the loading process, we have a method in our interface that sort of handles that. And it's not too complicated. Same thing with our definition manager. Pretty much for each kind of definition, maybe you want to say, I want to add this type of definition, I want to add this type of definition. That's not too complicated, and I can resolve imports within my definition manager as well. So after we got it working, we were able to load modules. We were able to load programs from scratch with this model. It wasn't too complicated. It worked pretty well. But some of the things were a little bit tricky. Incremental loading was messy because in order for incremental loading to work, I'm going to go back to this picture. We're delegating the responsibility of managing the semantic model to our module manager. But when we're incrementally loading, when we're like adding a method definition while the program is already loaded, for example, we're managing one definition, but we're talking to the module manager, but that's a definition level change. So what we ended up doing was having to basically re-implement the entire definition manager interface in the module manager, which was sort of hacky. So the module manager was essentially delegating most of its activity to the definition manager, and that made things really confusing. And there were times where I was thinking, well, really, what's the distinction between the module manager and the definition manager? Because they seem to be doing the same kind of things. So one of the big discoveries that I made while sort of wrestling with what's the difference between the module manager and the definition manager was the two roles are actually very distinct. And I sort of briefly mentioned it earlier, but it wasn't really clear to me until after I had something working and I wrestled with it for a while. So the module manager handles things at the module level. So it handles what do the subsystems know about, what do the programs know about, those types of module level changes. And the definition manager handles the definition level changes. What do I do when I actually install a method definition? What sort of things do I need to do? I need to build the scopes for the method. I need to, when I add a class definition, I need to make sure that it knows about its instance variables, that those scopes are set up correctly. Those are two very different levels. So I defined some terminology to help me understand what was going on, and this made things much more clear. So we have two words that, and before, because I didn't have the verbiage right, that's why I was confused as to what the difference between the two were. So we use adding a definition by saying I'm going to add a definition to a module. What I mean by this is I'm going to add a class definition to a subsystem, for example, which means that the subsystem specification is going to change, and that's a module level change. So what happens is in your tools, when you add a definition, the subsystem then knows about the definition, and then the module is then changed into a specification. So that is distinct from installing a definition. When I'm installing a definition, that is when I actually build the scopes. That's when I actually decorate the module with the right artifacts from that scopes. So there's a distinction, and it's a little bit tricky, but with this verbiage, it's easier to talk about. So,
Speaking of that,
yeah.
what is the distinction between module and subsystem?
Okay. So a subsystem is a module. Subsystem is a type of module, but not all modules are subsystems. For example, we have a program module. A program module is a module. A subsystem module is a module. We also have clusters.
And both of those are entire namespaces.
Yes, both of those are entire namespaces, and those are sort of like our big namespace, like big scope, global scope modules. We also have, I haven't even talked about clusters or packages yet, but those are two other types of modules that we have. And so a module is just a way to separate our definitions, basically, and a subsystem, into some sort of, partition, yeah.
So it is a form,
Mm-hmm.
and if we were going to use Rebecca's stereotypes,
Mm-hmm.
we'd say that subsystems and clusters are structurers,
Mm-hmm.
and that they're structuring a collection of packages. The packages partition the definitions of the subsystem. So if I'm talking about a subsystem, I can think about it as here's a global namespace of uniquely defined things. That global namespace is partitioned into packages, and then I have a number of views defined upon those packages that are called clusters. So there are many ways I can cluster the packages that make up a system. And if you've used VSE, it's clusters and packages.
Yeah.
Yeah. And so the way a subsystem will structure its namespace is it has a top-level cluster for all the definitions of that namespace, and it has its set of imports.
Mm-hmm.
And those together close the namespace.
Mm-hmm.
So a module for us is any kind of scope on your program.
Oops.
So there's the program scope, there's a subsystem scope. Both of those are global scopes. And then at a smaller level, clusters define a scope and packages define a scope, but they're not closed namespaces. And then our tools respect it. If you've selected a cluster, you see all the definitions in that scope.
Mm-hmm. Yep.
So let me see if I got it right.
Sure.
So subsystems, programs, and so on are modules.
Yes. Clusters are modules, packages are modules. 4 kinds of modules.
Okay.
Programs and subsystems are global modules.
And clusters contain
Specifications, references to other clusters or packages. And as such, they then define a view upon a subset of the module, the packages that belong to the system.
clusters cannot contain subsystems?
No. No. So subsystems are topologically sorted and live in the program.
Okay, so subsystems are the contents of a program, and then now you're saying the packages are the contents of a cluster.
Not contents of. Clusters just define a visibility relation on
Oh,
it.
right. So no, clusters reference packages.
Packages
Yes.
and other clusters.
Right.
Yes.
Okay.
So I have a subsystem is ultimately specified by a top-level cluster, and if it's got specific reference.
Wait. You said a subsystem is defined by a cluster?
The definitions of it. A top-level cluster in a set of imports for defining the closed namespace, the global namespace, right?
Okay.
Right. So I will need to have these imports. I need to have these definitions, and when I got those, there are no undefined references. That top-level cluster then has an abstract reference to a number of other either packages or clusters. That forms a directed acyclic graph. The interior nodes are clusters, and the frontier are all packages. And those packages partition the definitions in the subsystem.
I think I got it. Okay.
Okay, so with that in mind, what I discovered was
But come on,
yeah.
go back down to that slide. Let me zoom in.
Forward?
Yeah, come on.
Yeah.
No has or now has?
Right.
Now has. It's now
Yeah,
has. That's a
right,
typo.
yeah.
Yeah, I know. I just noticed that. Yeah.
Yeah.
We made these slides this morning.
Yeah, so I made them last night. So no, but yeah. So a subsystem has definitions.
It was this morning.
Sorry? Well, okay, fine. Technically, if you want to get all technical with us, yes.
I was thinking about semantics here.
We'll leave the bread sponge until 11.
All right. Yeah. So subsystems know about definitions by having clusters which contain packages which have definitions, which reference packages, which yeah.
So they're not like bundles.
They're not. Yeah.
Right.
Yeah. So there's a distinction between telling a subsystem know about this definition when it didn't before, and between saying now I want this definition, I want you to actually generate the build artifacts that definition generates. So for example, if I'm adding a class to a subsystem, I'm going to say this subsystem now knows about the class, right? So if I do that and nothing else, then I should be able to look at my specification for my module and eventually find that class. But that doesn't mean that my subsystem is loaded. That doesn't mean that there are any build artifacts for that class. That happens when you actually install the definition. And installing the definition means taking all of my class variables, and my instance variables and my class instance variables for that class, and generating the appropriate scopes, and then taking all the method definitions for that class and putting them in the appropriate scopes. And that's what installing a definition means. Yeah, distinct from adding a definition. So that was one of the discoveries that I made. Yeah.
You're saying that modules and subsystems have direct references. Clusters have indirect references.
They're all indirect references to definitions. So the only thing that's really contained.
No,
so,
I mean, so you have a program has a list of subsystems.
Okay, so repository subsystem defines a module specification.
Sorry.
This is our abstract reference.
Yeah.
So a program contains a sequence of subsystem reference specifications.
Do you want me to pull one up? And we can look
Yeah, why don't we look at one?
That's a good idea. Yeah, that's a good idea. Yeah.
Because I ended up thinking, the thing that in as much as these things are list of, so I was thinking, okay, so if they're all forms, kind of circles, you know, well, so what's the, I mean, it seemed to me was the type of reference that, in other words, the meaning of making a distinction in these forms is somehow different, and that's why you have a distinction there. Is that so?
I didn't follow that.
You have these forms, you have programs or systems that they quote have things unquote.
Yes.
Right. What I think, when I'm starting to think that the difference is between, say, a subsystem or a program,
Okay,
and
so
a cluster or a package.
I can't
or,
make that.
or like a cluster.
Can you
is
make it
that
bigger?
Making a distinction in these forms
I can
implies
zoom in
something.
or...
Well,
Something else.
okay,
The act of reference
more.
is slightly different.
Well, if we
Do you want to look at something small?
Yes. The distinction is
What?
Like
specified.
simple or something small?
Okay.
So,
We
right.
can.
Yes.
Do you want me to do something else other than anti-test record?
Yeah, it gets too much stuff.
Too much stuff. Yeah.
Like,
Like
if it takes
Delta
up the
Blue is
whole...
something like that.
Yeah.
Do you have Delta Blue loaded?
Yes.
And let's look at a subsystem first. Delta Blue subsystem. Okay, make that big. Okay, so here, the root cluster, each of these messages, so the message root cluster name colon repository name colon will create a module specification, which needs a repository name, a module name,
So you're
and
saying-
optionally a branch revision tag.
So root cluster there means roughly module?
Root cluster means that's going to be the root of the DAG, whose leaves, whose frontier, are the packages.
So you're just creating the clusters, and then I suppose that some other program will...
And so let's look at the underscore Delta Blue underscore cluster.
Uh-huh. Okay. Sorry, maybe
And so-
you didn't expect me to ask this question.
Oh no, that's fine. Yeah, so here you see here's the root cluster. It
Right.
adds references two packages.
Right.
But what it contains are specifications that are resolved in the context of the repository volume. So all our revision branch information is stored in the repository volume for this project.
Yeah.
And you use those names to go track down the distinctions. in the
And those
repository.
names are resolved in the context of the repository
Right.
volume for the project.
Right, okay.
And then they'll resolve unambiguously through the working copy.
Yeah. So there are different representations too, and that's one thing that makes it confusing. So when we're looking at specifications, for example, subsystem specification will list a top-level cluster specification. When we resolve that subsystem, we get back a subsystem object that has a reference to that specification, and then when we load that specification, that cluster specification, now the subsystem itself has an object, reference to an object that is a cluster object. So there's different representations that are...
The structure of distinctions remains, and the kind what crossing means changes.
Yeah.
Right, yeah,
Mhm.
okay. Right, okay. Yep.
Back to PowerPoint.
So there are forms.
Yes.
Yeah.
Students.
Everything. So, So another discovery that I made is that installing and uninstalling definitions are different. They're not necessarily inverse relations, meaning that when I'm installing a definition, it involves building the scope. But it also may involve a couple other things. I'm also going to be adding any symbols to the global table. I'm also going to be potentially compiling a method. Those things, I don't want to remove symbols from the symbol table when I'm removing definitions, because those symbols might appear elsewhere, or might appear in other places, and like, well, I'm not going to decompile the method. That doesn't even make sense. And then uninstalling a definition means removing it from the scope, but it also, I need to ask myself the question, what else did I break by removing this definition? If I remove a class definition from a fully loaded program, I may have broken a bunch of methods that have already been compiled that reference that class. So I need to go through and figure out what all did I change. And now this is not connected anymore. Yeah, so I need to figure out what all I need to change after I remove a definition. So, which led to the, that's another discovery. So this led to sort of thinking about, should I be actually installing and uninstalling these definitions in the same place, since their behaviors can be so radically different? So I was sort of thinking about that. And that also led to another discovery, which was that incrementally installing is very different from loading a program from scratch. So when you take a program and you load the whole thing, looks very different than just loading one definition at a time into a fully loaded subsystem. And you can do it the same way. You can take a program and load the whole thing one definition at a time, but you're going to get a lot of errors in the process because you're going to be loading one thing that depends on another thing that you haven't gotten to yet. And like that's confusing, and that adds a whole layer of complexity that I didn't really want to deal with. So by treating incrementally installing and as a distinction, as a different process than loading a definition from scratch, then that simplified things as well. So this is something that this is sort of like the next wave of the loader. So before we only had these two, right? So the module manager was basically the way that you got anything done was by going through the module manager, change this definition, load this subsystem, whatever. And then the module manager would delegate the pretty much everything to the definition manager. And the definition manager was like sort of in charge of doing everything. And that was not good. So here we have a much more clear responsibilities between these different, I don't want to call them subsystems because that's confusing, but these different aspects of the loading process.
Call them centers.
Centers, I like that. So now the responsibilities are much more clear. So the module manager still, his responsibility is to maintain the structure of the semantic model. The keyword here is structure. It's maintaining the structure. It's saying these modules have references to or know about these other modules, and that's pretty much it. And then it delegates all the definition level changes to the definition manager. Now, before the definition manager actually did the installing and the uninstalling, but since they're entirely different processes, the definition manager is only responsible for saying what definitions do I actually need to install and what definitions do I need to uninstall. So you can think of an example of when I'm switching branches in my repository. I might have the same modules, but they might have completely different definitions within them. So the definition manager is responsible for saying, okay, I have these set of definitions that are from the old branch. I have these set of definitions that are for the new branch. Which ones do I actually need to install or uninstall? That's what the definition manager is responsible for. And then I have definition installer, actually does the installing, builds the scopes, compiles the methods, adds things to the symbol table, blah, blah, blah. And then the definition uninstaller is responsible for removing them and saying, okay, what did I just break? So that's it. Yeah. So the results of these different discoveries allowed me to refactor the whole loading process, made it a lot more clear to understand who exactly is responsible for what types of things. And I removed a lot of duplicated code, because before, basically, anytime you wanted anything to happen, you had to say, module manager do this. And then the module manager was basically just saying, definition manager do this, so there was really no point in having two distinct objects. So I was able to remove a lot of duplicated code, and it makes a lot of the more complicated program changes feasible. So now when I am actually removing a definition, I have a clear object that's responsible for uninstalling a definition and doing that process. Whereas before, the module manager was sort of responsible for installing and uninstalling, and it was complicated because there was the one guy doing lots of different things. So this simplified it a bunch. So there's still a lot of things that need to be done in the error handling. Well, in the module loading in general, one thing is the way errors are handled. Not all. Currently, we're supporting. We've currently implemented any kind of like compilation errors. If you try to compile them, if you try to save a method that won't compile, that error will get caught, shown up in the IDE, and you can click on it in the IDE. And then when you fix the method and you save it and it is able to compile, then the error goes away. And that's really nice. But there's some other errors that were sort of just getting thrown and they're not actually being caught. Errors like module structure errors. For example, if I have subsystems importing from other subsystems that they import from each other, which one do you load first? You can't tell, so that's not allowed. Right now, if that happens, who knows what's going to happen? It'll throw an error, get a walkback. We do throw an error, yeah. So you get an error, but obviously we want the IDE to be able to catch that error, display the error to the user so that you know what's going on, and then provide some sort of interface to fix the error. Name conflict errors, we don't really have that. We don't really support name conflict errors. We catch multiple declaration errors, but it's not entirely working 100%.
It needs more work.
It needs more work, yeah. Also, I mentioned in the talk yesterday that the order in which subsystems are loaded in is determined by the order laid out in the specification. That's not actually the way it's currently implemented, but it's the way that it should be implemented. The way it's currently implemented is a little bit more complicated. It does like a full topological sort to figure out, okay, what subsystems depend on other subsystems, and then it loads the subsystems that don't have imports first, and then loads all the subsystems that it can that depend on the subsystems I've already loaded next. And it's a little bit smarter than it should be. What it should be is I should just take the subsystems as they're laid out in the specification and load them in that order. And the reason for that is because we want the user to be able to be in control of that, and that because that's the same order in which our initializers are fired, there might be situations in which we want our one initializer, subsystem initializer, might affect another subsystem initializer, and we want them to make sure that they're in the right order. And if we're sorting them, there's no guarantee that we're going to sort them the same way every time. But if we simply load our subsystems in the order that they're laid out in the specification, we can guarantee that the initializers are going to be fired in the right order. So that needs to be changed. Installing and uninstalling definitions doesn't always recompile the affected methods. So if I uninstall a class from a subsystem, we have ways of figuring out what methods are being referenced by that class, but we're not actually doing anything about it. We're not recompiling those methods and those kinds of things. That needs to be changed. And also, when you check out a branch, right now it doesn't do anything. Right now, the program model remains the same. It remains the same way that it was when you loaded the program in the other branch. But when you change branches, what should happen is you should say, I need to migrate this module, as Alan would call it, migrate this module to the new branch versions. So those are some of the things that need to be changed, some of the things that need to be refactored. And that's pretty much it. So overall, it was made a lot of discoveries, and it's one of those things that John said. The reason waterfall doesn't work is because you can't know everything about the system that you're designing until you start designing it, because that's when you make discoveries, and that's when you learn what your system should be, what your system design should be. Because we actually did quite a bit of design up front, and that's how we got that simplified model, and we did a lot of design trying to get there. But it wasn't until we actually got it working, it wasn't until we actually implemented that we realized, oh, these things are distinct from these things, or, oh, this thing is different from that. So it doesn't really matter how much design you do up front. Well, it matters a little bit, but you can only do so much design up front. So the process of actually getting something working is more important than making sure everything's perfect before you start. So that's the big takeaway. So, all right. That's. Yeah, are there any questions?
You said build artifacts.
Yes.
What are those build artifacts?
Sure. So the build artifacts that I'm talking about are, I consider error to be a build artifact. It's in the process of building that you come up with an error. So I tell the module, hey, there's an error. And so that's an artifact of building. The other build artifacts are the scopes that you need to set up in order for the compiler to know like where things are at. So when the compiler is compiling a method and it has a reference to a class, where does that class come from? It's just a name, right? In the source code, it's just a name, but it needs to be bound to some sort of definition somewhere. So I need to be able to. So building those scopes is the build artifact. So a subsystem module has a global scope, which is one build artifact. And the reason it's a build artifact is because I take all the class constants and variable definitions that are defined in the subsystem, and in the process of loading the subsystem, I take those definitions and I bind them to their appropriate names in the global scope. So the global scope is an artifact of that building process. So it's a build artifact. So.
But build artifacts, for instance, does not necessarily mean. Well,
Semantic decoration.
Semantic decoration is a better name for it, and maybe build artifacts is not the right name.
I was wondering if you included, say, compiled methods that are installed and active in the system, although I'm not sure.
There is no such thing.
Since there's no system, that doesn't really make sense.
But it does mean compiled methods up to intermediate representation.
Yes.
Which
Compiled.
means,
Mm-hmm.
Which means, for example,
Yep.
in a method, there are scopes for all the blocks
Mm-hmm.
in a method. And when you look at the bindings of those scopes, it says, this temporary variable in the block is bound to a heap activity because it's captured by the block. So it's going to be in the second environment down and third index up.
Mm-hmm.
Right? So in each block, you have your own set of bindings for where does the runtime find that value in either the heap allocated scope chain or the stack allocated.
And you're distinguishing loaded from installed because, just out of curiosity,
Well,
there has to be something.
Well, loaded. So loaded means installed. Yeah, loaded means installed. There's no distinction between. Well, yeah, loaded is more of.
Added and installed. Sorry.
Yeah. The distinction between adding and installing is so. If you have a fully loaded program, right, and you open up a browser and you add a new class to your loaded program, a couple things need to happen. The first thing that needs to happen is whatever module that you're looking at, that class needs to be added to the specification for that module, which means that I actually have to take the module and actually add the class to the module and then write out the specification to disk, so that when I close my loaded program and I reopen it, that class is there, right?
Okay.
But that's different than actually installing the class, which happens when I load the program. So when I take the program specification and I load it up, that's when that definition will then be loaded, right? But I'm not gonna every time I add a class to a loaded program, I don't want to have to shut it down and then open it back up for that class to appear. I want to load it right then, right? So that's the distinction between installing and adding. Okay. You want a mic? All right.
Stop just get the whole.
The whole layer.
Well, hello. I'm Adam, and I've been kind of working on the runtime aspect of Modtalk, because once these guys create objects and all these code everywhere, somebody's got to evaluate it. So, as I mentioned in my presentation yesterday, there's kind of like you have the evaluation system, and when you look outside of the evaluation system, at the evaluation system in the object space, you kind of have objects, and they exist in grades, but there's not really a clear, this object is in this grade. That's mostly internal to the object space. But this is what it looks like kind of outside of the system, but here we're going to delve into the object space. So, let's see here. slide. So I mentioned yesterday there's this abstract machine, and this is just the abstract evaluation system. So I'm not going to go over that, but just a quick thing. We also have a global to the entire runtime an interrupts flag register, which is just how you assert interrupts when an interrupt has happened. So this is kind of like a high-level overview of how the evaluation system works. You have the code component here, and there's multiple different ways of executing code. For example, the native, the threaded, the interpreter. And these just work together with the object component, and that has the garbage collector, object allocator, and object space. So they kind of communicate with each other to evaluate programs. And this is all above the operating system. So first up, we have the basic memory model. You have the object space, which is global to the entire program. And this contains a set of grades. Grades correspond to a generation. You just have longer-lived objects and higher grades, short-lived objects and lower grades. And you collect the lower grades more often. Each grid has a set of chunks. A chunk is just a block of memory. And it's nothing really special about it. It's just a linked list of just blocks of memory. And each chunk has a set of objects. And an object is a Modtalk object, an instance of an object. So those are the main three things that we have. We also have a couple other things, for example, scraps, which are just spots in the chunk, and big object headers, which are types of chunks, or scraps. I'll cover those in a minute. So the object space. The object space is defined by these variables here. The object space has a list of the grades. It's just an array, so we have 7 grades. A number of grades. So when we have 2 grades right now, it's only set to 2. This is just for metrics and statistics. And we have 3 sets of basically lists, linked lists, and they act as caches. So we have a list of free scraps. So if we ever need a scrap for a big object header, we just pull it off of this. If we're done with the big object header or some sort of scrap, we just put it back onto the list. And these just serve as a quick way to get these, because oftentimes we're creating a bunch of them, releasing them, and creating them and releasing them. So this prevents us from having to reallocate a bunch of memory. And free chunks, they serve the same purpose. Chunks, they're just blocks of memory. So we need to be able to allocate them and acquire them and deacquire them often. Because every time we do a generation, like a garbage collection, we're always grabbing another set of chunks, and then we're returning the chunks. Because we do a semi-space flip, where we just copy all the objects to a new chunk and release the old chunks. So it just serves as a fast way of getting them. And a free stack segment list. Since we have a bunch of stack segments. In the future, when we have multiple stack segments, we'll just use those.
Yeah, but we're not using that yet.
Yeah. No. And again, we have this global to the entire runtime, the interrupt flags. And this just contains what interrupts have been triggered. So what is a grade? A grade is defined as a set of chunks. And this chunk list is a linked list of chunks. And the...
Thank you.
Yeah. So it's a linked list. So we can enumerate over it. And we also have a reference to the tail of the chunk linked list, which is where any new objects that we allocate, it's going to go into the last chunk. So it just allows us to directly allocate it into the latest chunk. Also, we have a remembered set, and this is just a list of objects that contain references into this grade. So if we have a higher grade, and this object points to a grade in grade 0, this object will exist in the remembered set. So when we're enumerating over this remembered list or remembered set in the garbage collector, we can immediately find all those references. Also, we have a set of big object headers. It's a linked list again. And if we have any big objects, I'll define those later, but we'll keep track of all the big object headers in the grade. And this allows us to find these references in these headers and automatically clean them up as we need to.
So as a quick sort of overview, what that means is if you have an object bigger than a certain size, the body of the object is remote. It's mallet. The only thing that appears in the current grade is the normal header and a pointer to the big object header struct, which means we can fit more objects in the space before a scavenge, which means more things will have died by the time we actually do scavenge. And because bigger objects tend to live longer, they're allocated in fixed memory, and we need to keep that list of big object headers so that when one of them dies, we know what thing gets freed.
Yeah. So, sure. Yeah. Yes. Oh wait, no, this one.
You said the remember set holds the objects that have references into the space.
Yes.
Does that mean references from objects in any other grade or just higher grades?
Higher grades. Yes.
Okay.
If, say, we're looking at a higher grade and an object in that grade holds a reference to a lower grade, it will not be in the higher grades remember set. It will be in the lower grades remember set.
Right.
So when we're looking at a lower grade, we have no way of discovering what objects point into this grade. So this remembered set just serves as a way to find all the objects that hold references.
And when we see the object header, you'll see how we mark.
Yeah.
So maybe stop till we get to the bits in the header.
Yeah. Yeah, I'll go into detail more on this stuff,
I
but
just wanted to know
yeah.
if in your implementation, remember sets were stacked as a ladder or more like a whatever.
Okay. And yeah, so yeah, this just contains the references to the remotes. Okay, and then also we have the number of chunks we've currently allocated in this grade. This is just mostly for statistics, and as I go into GC metrics later, it'll be useful. So this is a chunk. A chunk is just a block of memory that contains objects. So we just have a bunch of these chunks per grade. And how it works is you have a block of memory, and at the beginning of that block of memory, you have the chunk header. And the chunk header has a couple of things. It has a size, basically how big the chunk is, a pointer to the next available free slot in the chunk. So anytime you allocate a new object, you just go to the use pointer, and it's pointing to the end of the chunk, and not the end of the chunk, the next available free slot, and you allocate the object right here. And yeah, so then it's a linked list again, so it just points to the next chunk. And objects are allocated sequentially after the header. So you have the header, and then you kind of have the body. So all the objects in the chunk are allocated on 16-byte boundaries?
Yes.
Yes. So we always allocate them on that boundary, that alignment for performance reasons due to cache line. We hope it's the case. In the future...
The current mythology.
Yes. So some of the stuff that we plan to do in the future are kind of collect statistics on this and verify that this is the case. So everything's just online, and yeah. So this is kind of what we have. Two main object types, I guess, or sizes, structures of an object in Modtalk. You have a small object and you have a big object. Currently, an object is small if it has less than 255 slots in it. For example, if it's an array, if it has less than 255 items in it, or if it's an indexed object, it has less than 255 instance variables. And if it has more than that, it becomes a big object. So how a small object works is, this is what an object looks like. You have the object header, you have the method dictionary, and all the slots. And this entire object block is inside of the chunk. So it's all inline in the chunk. But if you have a big object, what happens is you have an object header and a method dictionary, like before, but you have a pointer to this big object header here. And every single grade has a reference to all the big object headers that exist in that grade. And this big object header is a linked list again. So it has a reference to the next big object header. It has a pointer to the base object. And as we're doing verifications to see if any of these objects have died, we'll just look at all the big object headers, go to the base object, and see if it's died. If it's died, we'll free all this memory. And it has a pointer to the body. And this body right here is a remote body. And we allocate it dynamically using malloc and free. unlike chunks where they're mallet and they're never freed. And the slots for a big object are located in the remote body. And we also have a size. Make sense?
Which is the size of the mount.
Yes, the size, yes.
That's the size of the
Number of slots. Yes. Okay.
Yeah, that's correct.
But other objects point to this part in the chunk or the scrap.
So unlike VSE, which pointed at the below the header. So in VSE, you point at the effectively the small object header, and you might have two. No, you pointed right at the body.
Yeah.
So you'd have a header before, you have a pointer at the body, and the rest. Here, our objects, our OOPs, are pointing right at the first byte of the header.
Okay.
So an OOP is always pointing at the header. So the primitives will hide, or low-level code will hide. Is there a remote body? Is this extra level of indirection occurring?
Okay, but then they are all pointing to the chunk part.
They point to a position in the chunk.
They're allocated, so the chunk is the arena.
Yes.
Yeah, but I mean other object that points to that object.
This point object?
Another object that points to a different object will point to the
Another object will point to this right here.
Okay.
This object. It'll point into the grid, the chunk.
And into the head, to the header.
At the header,
Always point
in
to
the chunk.
header.
Yes. Yeah.
So your at what primitives have to know the difference between big and small objects.
Okay.
And that's how they hide the remote access for the big ones.
Yeah. Okay. Cool. So the object header. So we have different formats or different layouts of it, depending on whether the platform is little endian or big endian. And one thing we make sure is so in 32-bit, or these things are always 32 bits, but in in 64-bit platforms, this will be one word, but in 32-bit platforms, this will be one word. And we always make sure that these things are always aligned, like the flags are always aligned with the 14 pointer.
And the reason for that is using the GC mark.
Yes. Yeah, I got it in my next slide.
Oh, okay.
Yes. So here's what it actually looks like in the bit alignment. So what happens is you have, this is the 14 pointer, and this is the hash right here. So one thing we do is we have this GC mark bit right here, and it's a single bit. It's set to 1 if it has not been moved, and 0 if it has been moved. So if the GC mark bit in the object is set to 0, we know that the forwarding pointer points to a new position. And we need to update our reference to point to that new object.
And what was suggested by your picture, the first word is a union of forwarding pointer or control word hash.
Yes.
So if the GC mark bit isn't set, it is a forwarding pointer. Right, so we just stomp on the first word of the OOP with the forwarding pointer.
Yeah, because this is...
Because all our pointers are aligned, we know the GC mark bit will be clear if the object's been forwarded.
Yeah. Okay, so this is all in the same... They're unioned right here, and this is like 64 bits. So the GC mark bit is always positioned to be the least significant bit in the forwarding pointer, and that allows us to take advantage of this. So when we're compiling the runtime, we have a bunch of if defs to see which endianness it is and which, if it's 32-bit or 64 bits, and we'll make sure that this mark bit is always aligned with that. Other flags that we have in the object header are we have 3 bits to specify what grade it is in. So we know if this object is in grade 0 or grade 7. And we're using that a lot when we're traversing the object graph to see should we work with this object or not. We also have 8 bits that specify the remembered set, which remembered set this exists in.
Or which remembered sets. It might be in multiple remembered sets.
And that's why we need 8 bits for this. So if an object is in a higher grade and it exists in the remembered set of a lower grade, we'll set the bit to 1 in that one. And when we're storing variables into this thing, we can do like a store check to see if it's already in the remembered set or if we need to add it to the remembered set. And we'll just check the remembered set right here, like this bit fields, to see if it's in the remembered set. We also have num vars, basically the number of vars it has. So if it's bytes, if it's like a byte array, then it'll specify the number of bytes. Or if it's like an indexed object, the number of variables will just be the number of instance variables. And we have a hash format, which just specifies if there is a hash or not. Like if we, some objects we lazily hash objects when you request the hash, or some objects, for example strings, we hash them ahead of time. And you'll just check the hash format to see if it already has been hashed or not. We also have 4 bits to specify the type of the object. For example, there's byte arrays, strings, indexed objects, indexed parts, that kind of thing. So the type will specify whether it's big or not, and that's how we'll know whether we need to go to the remote object or not, the remote body. And all the primitives will be checking this type to see what type it is, so they know how to handle it. And then you have the hash. Let's see what's next. Okay, so how does the garbage collector work? This is like a very basic overview of what steps it goes through. First, it visits the registers, then the stacks, and then the remembered set of the current grade. And these are kind of our GC roots. These are all the roots that we'll look at when we're doing a collection. Then we do a linear walk where as we're moving things over to the new chunks, the new space, we'll just keep walking and walking until the new chunk space stops growing. And at that point, we know that we visited all the objects in that grade. And then after we do that, we know we visited all the objects in that grade. Then we can start doing collection, or like the finalization. So remotes, what we'll do is we'll go to the grade, look at all the remotes that we have, and check to see that all the objects have survived. If they did not get copied, that means they died, and we need to clean up the remote bodies. After that, we do weak references, weak objects. Since we know what all the weaks are, we'll verify that, we'll see if they've died or not. And ephemerons, we have a list of all the ephemerons in the current grade, and then we'll just go through them, see if any of them have died, and if they have, or if the reference that they hold on to has died, then we'll make it strong, and we'll schedule an ephemeron finalizer interrupt as soon as Kurt gets that working. But that stuff, it supposedly works, but it doesn't pass it off to the program yet. So some of the things we're doing is we have some metrics. Basically, I added some statistics collecting in the GC itself, and basically I'm collecting how long it takes to do each step in the GC, and we're going to use this later to optimize it. So here we see how long we've spent in each period. For example, registers, we didn't spend much time actually looking at the registers, and most of our time was spent in the linear walk. This is kind of what we expected, but we can see that stack is the second biggest thing that takes time to do. This is also some other stuff that we collect, basically time, and we can see the sizes of the grades before and after collections. So we can use this for later tuning and optimizations. So you can see like there was a GC here, and we freed this much objects at each point. So what actually happens is for every GC, we just write to a comma-separated value file and just some metrics about it. So you can see what grade it is, how big it was before, the size of the remembered sets, and that kind of stuff. And we'll use this for later optimizations. As I mentioned in my slide or my previous presentation, we can collect per object metrics, the number of attributes, like attributes about it, what type it was, how big it was, what grade it was in, and how long it lived. And this is all written to another file that we can conditionally enable either one of these statistics collecting tools. And what happens is it just writes to a file all this data, and when it was created and when it was killed. When we realized it died. And all this stuff, basically I'm going to in the future hopefully start to find patterns in this information. And so earlier when I mentioned like the size, currently if it's less than 255 slots, then it becomes small. These metrics will allow us in the future to see if 255 is a good cutoff to make it small or big. So we can see if there's a certain point where objects live for longer than objects smaller than that.
Well, some of the things that we're not clear of,
Yeah.
I mean, we get a couple of advantages by using the remote big objects. It means we get a lot more objects in a grade before we have to scavenge.
Yes.
But we have that extra level of indirection to get to the remote body. If we make it cut off so there are fewer remote big objects, does that mean we're going to be collecting more frequently? We just don't know.
Yeah.
But that's what we want to get some data points on.
This is what we plan to do with this data, I
But
guess.
we're looking at like scavenge times from like 2 to 12 milliseconds? Microseconds.
Microseconds, I believe.
2 to 12 microseconds.
I'm gonna go really miss
Sorry. Yeah.
Might as well manually.
Let me get my Crayola.
Anyway,
Might as well use a reference camera.
the collect time is purely a function of how many objects live. And the more objects live, the more bytes you have to copy to new space. And the more bytes you copy to new space, the more time you spend copying. And in a small object, you have to copy this entire object with all the slots in it. But in a big object, you're only copying these 3 words. And if we can find that these big objects live for longer, you will only copy these 3 bytes.
Yeah.
And you will save the time you spend copying all the bytes in all the slots. So we're going to use these statistics to find thresholds to make them big or small. What else do I have? Is there anything else? Okay, blame Kurt. So, interrupts.
Sorry.
Yes.
I'm not sure if I'm following what you say, but you said that when running can you go back?
Sure.
To the
Which one are you looking for?
one before this.
This one right here?
Yes. You say that when you are compacting for small objects, you need to move the whole object, and for big objects, just the header here.
Yes.
And you are doing measurements on this. But I guess that when moving big objects, not when moving them, but when collecting them, you will have more work on free. Okay? And most likely when you allocate them, you will have more work on malloc, because you are not reducing memory, you are asking the operating system for memory, and you are giving it back to it. Are you including that time in the measurements? And if you do, that time will change from one operating system to another, so the figures will be different on Windows and on Linux, for example.
Yes, they will. But the malloc and free will be part of the alloc and free, so the metrics will catch on the host operating system. So what that means is if we're looking at 7 targets, we'll have to run the metrics on 7 targets.
Yes. Right.
Yes.
And
Yes.
pick the
And that's what you have to do regardless, because you don't know.
Well,
And
I guess
those
that
operations are all one.
Yeah.
I guess that big N isn't hard coded, and maybe you
It's in the source code, but it's easy to change.
It's
Okay.
easy to change. It
And
depends
you-
on the number of reserved bits we have left in the object header.
Yes.
Okay.
So
Maybe
if we
it's a parameter you can optimize after you do measurements.
Yes.
for
Yeah.
several
That would be the
signals.
intention. Yes.
So
Yes.
it's not
But
an
we're
easy
finding
decision. You need to do a lot of
that
statistics.
it's really, really, really fast right now.
Okay.
This is not a bad thing. It's surprising how most of your objects are less than 255 instars or index slots.
yeah. So this is
Excuse me. What is fast? Malloc and free? You say? Is fast?
No, I did not say that.
Okay.
Malloc and free are slow and horrible.
Okay. That's why I asked the question.
Yeah.
Because that's what I think.
Relative to a heap alloc.
Well, I'm sure that I missed it because of our tardiness.
Yes.
Do you have a primary current development platform? Like,
We are
or
developing
operating
OS
system?
10 and Linux.
Okay.
But those are just the ones that we
Right.
added support for.
Well, I think
mean,
like Juan's concern gets much more germane on Windows.
Yes, it does. Yes, it does.
but that's yeah.
Ignoring Windows
Yeah.
because of those things.
Yeah.
But
But they are, it is,
It's
but
left as
part
an exercise for the reader.
Those are the things we need to be able to measure and document them.
Right.
And maybe someday you want to target something like Android.
Oh, yeah.
And who knows
We
what
actually,
you will find.
well, our runtime will run on ARM.
We've actually run it already on ARM.
Yeah, so
No, we definitely will. And for that, if we have to do something, pools, if it is, there's some small pools of certain object sizes that are frequent, there are strategies we could plug in invisibly, and that would be something that would be driven by actual data measurements, not, I think this might happen, so I'll write the code. So I'm trying to teach them, get it to work right first, and take measurements.
And there's no JIT, and so you don't have an issue with Windows 8, for instance.
Correct, there is no JIT.
It's just credit.
is it
Well,
necessary?
no, we do generate native code, but it's assembly.
Yeah.
That just compiles. We just run through the assembler.
Okay.
And does it make sense to make these choices platform specific, maybe, or
Until we have data points, there's no way we can know.
okay,
And so we'll not pretend to know.
it would have been possible to do it.
But we have the ability to do it, yeah.
Yes.
So that's what the point of all these metrics are. To see if there are differences between platforms, to see if there are patterns that we can act upon. So we collect all this information, and we'll later analyze it.
Yeah, so I'd say the big thing, I think some of the most interesting things about the garbage collector is that instead of a variety of different garbage collectors, there's just one scavenger, but there are 8 grades.
Okay.
And so your mutator check, each object header, you've got 3 bits telling you which grade do I live in, and then you've got an 8-bit vector saying which remembered sets am I in.
Okay.
So
Great,
in your
yeah.
store check, you can say, compare their grade IDs, and you know which is greater, to know whether or not you actually have to put it in a remembered set. And then you say, is that bit hot? And if it is, it's already in the remembered set, and I don't have to do any more work, and I can return from the mutator.
Yeah.
So we've got a relatively fast mutator check, even though we have multiple grades that we have remembered sets for.
So what's in the header? What's after numbers?
Numbars, yes, that's
So to the left of that is what?
just reserve bits. We have a couple bits here, reserve bits that we can use to expand or
For
that kind of thing. Yeah.
experimentation. If we want to change the size, we can reorder the bits in the header.
Yeah.
What's hash format? Is it?
Yes, hash format. We have a couple, 3
We can
hash
lazily
formats.
allocate hashes.
Yes.
Oh, so you put 0 and whatever.
So it's just 0 until someone actually looks.
Right.
And so there's one of the formats is no hash assigned. Okay. So then someone asks for a hash. If it's an OOP object, we have a linear feedback shift register that generates one of these wildly distributed polynomial values. If it's a symbol, we have an FN1V hash that runs on the symbol, and the symbol's just stored. If it's a string, we always calculate the hash.
We pre-compute the hash, right?
Not for strings.
Not for strings. Strings are beautiful.
Compiled objects get a hash assigned.
Compiled objects get a hash. OOP objects get a hash assigned. Byte objects that are mutable always calculate their hash. And immutable byte objects calculate it once and store it. Except unless they're in grade 7, generated by the compiler, we just generate the hash at compile time and put it in.
And we're still deciding whether or not we want literal strings to be mutable or not.
Yes, and right now our literal strings are mutable, and we're thinking about whether or not we want to make them immutable, but that's a separate story.
Why is there a 0 at the end of the, so you have in the hash word, so 0, 1, 2, 3, and the last one is 0. But why 0 not that?
Oh, it doesn't have to be 0. It just when I was typing in, it becomes 0.
Because
Yes, and 0
no, because what's your small integer format like?
Small integer.
The mark bit is set for a small integer, so we have 63 bits available for small integer.
and we bit shift over one, and Mark.
Yeah,
But
the
it's
low bit
small.
Is our
1 terabit?
oh, we're only using one for our small int. We have, because all our objects are 16 byte aligned, we have more bits we can use if we want to do small floats or that. We're not doing floats at all yet.
That's fine, but the small ints are basically they have 1 target.
Yes.
So actually the hash field could be 63 bits too, because why return a large integer, say.
It could be, but since it's part of the control word and the low bit is the GC mark bit, it's either going to be a forwarding pointer or it will look like a small int.
No, I mean the hash field.
Yeah, well, on 64-bit, that is, the hash field is part of that word.
Yeah, this is one word on 64-bit. On 32-bit, this is one word. This is one word.
And so 32-bit, we might have to go to a 63-bit hash. There are 32-bit issues to make it look like a small int.
32 bits might be a 63 bit.
What?
What?
You mean 31-bit hash?
Yes.
Okay.
What is it? Yes. Professor Singh. Thank you, Professor Boris.
Yeah, right.
Cool.
We trust you way too much.
All right.
But we learned something.
And we questioned.
I was tempted to ask you why we should.
No, no, it wasn't a question. It just dissonated. It's just dissonated, right? It's like, where are the 63 bits?
Yes. In my mind.
Yeah, when we hash it, we're just going to get rid of all the other flags.
It's 4 o'clock. Do we want to take the break that's scheduled?
Oh, it's
I
already
thought it was.
Yeah.
Oh yeah.
It's
Okay.
4. We were 2:30 to 4.
Yeah, we're asking a lot of questions, you know.
5.
You guys got to stop asking me so many questions. I got to move here.
So your slide? Can you wait for just a few more minutes, guys?
I don't know how long it'll take.
I know, but yours is going to be fun, right?
Sure.
I know you're laughing and chuckling and looking at me going, all morning, so
So this is how an interrupt works. Cool. All right.
Well, no, this is how an interrupt works.
Yeah.
This is how an interrupt works.
The anonymously described interrupt.
Thank you. Well, that was supposed to animate in, but so I'm talking about when I implemented exceptions. So we got to a point where our system was working, the compiler was doing what it needed to do, the runtime was, we were able to build the semantic model, and we wanted to start building real programs and actually use SUnit. So we initially implemented SUnit using block returns, but we wanted to get exceptions. So this is our journey to exceptions.
An exceptional journey.
Yeah. Oh, yes, with stick figures. Okay, so I was just going to say, here's John's executing on the stack here. He's at the top, and he executes a block return. He likes being up there, and then all of a sudden he teleports. He's somewhere else. We skipped a bunch of frames. Let's see. Okay, so the first thing that when you implement block returns is our first implementation. We just skipped down to the method context, ignored intermediate frames with ensure and if curtailed. So now we get to a point where we actually do need ensure and if curtailed. And so we hit an ensure, and we're like, what do we do? So the first thing that we implemented was in the VM. And so we inserted intermediate frames, and it looked a little like this. So you have this ensure frame where there's a block, and then we craft this special reentry frame. And then we execute the block on top of that. When the block returns, we're entered back into our runtime, and we're able to continue processing the stack. Information for that processing is stored in that frame. And so at first, this was okay. but then it started getting smelly. And at 250 lines, it wasn't working exactly how it needed to. And I didn't want to deal with it anymore. So there's John. So we started thinking about what it should look like. And I don't remember the comment John made, but it sparked something. And I'm like, what if we do it in Smalltalk? So, yeah. So I started thinking, what should it actually look like, and what do I actually need to do? The first thing that came in was our stack. It's just a hunk of C memory. It's not objects. We're not doing a linked list of frame activations. So John's like, what if you make an external address subclass? And I'm like, what does that even mean? And so after our day of thinking about it, all of a sudden something clicked, and I'm like, oh. So I moved on to my next problem. How do I find an ensure and if curtailed frame on the stack? First, what we were doing was marking the method. So we have 3 low bits that are free. One of them is used for small integer, and so I started marking the methods. This is where the VM code, started getting gross. So I started marking these methods, the bottom 3 bits, and using that to determine if I need to do something. So when I started working on thinking about how do I do in Smalltalk, we looked at VSE and saw that they use a special method to mark their frames. So that's what we did. And so we added this value marked, does the same thing that value does, but it gives us a separate distinction to look for. Then the next thing that we needed to do was, if you have a block and you return, you have to return to the right activation of the method. So we weren't really sure how to do that initially. Our first implementation did not do that. It found the first method on the stack and returned there. It's very good. So we decided that we already have this heap allocated environment slot. If there's a block return, we'll just allocate a marker end at the end. It has no slots, and it just sits at the end. And so that's how we detect if the method is the right one. And this is where the fun began. How do you actually return to that method? Well, magic. It's actually a primitive, but so this is my first
return to or from?
From.
Okay.
Yep. So you need to return that value from the method. Yeah. Okay.
Just
So.
Just to drill, kind
Yeah.
of point down.
Yeah. So I started thinking about it, and one day I wrote this. So the first thing we do is we grab the contexts. So we've objectified our frames. And now we need to detect if the termination is there. So that's a primitive. Then we need to check if it's value marked. That's a primitive. We need to grab the first argument if we do find an ensure or a curtailed frame. So if we're in a context that's value marked, we need to grab the previous context and evaluate the first argument.
Which will be the argument to ensure
Yep.
colon or forget.
So it'll be the block that was that argument. If it's not the case, let's just continue. Once we do find the termination context, we'll return the value to this context, from this context, sorry. You're probably seeing some issues here.
No, well,
Okay.
not necessarily.
Okay.
I'm trying to understand how this works.
It's magic.
The slot in the stack that you're
Mhm.
marking,
Yep.
right, to be able to identify where it is.
Yep.
What is in that slot? Like, what's the content of that slot?
So it's not just a slot, it's a
Okay.
frame. The frame has a method,
Okay.
and that method is our value marked method. So we have ensure, a block, and we say self value marked instead of value marked, or self value. That activates the value marked
Self is the
frame.
context in this case.
Self is the context. So you're some block and ensure some other block.
Mm-hmm.
You say self value to evaluate the original block. Instead, what we do is say self value marked.
And value and value marked have the same implementation.
Yes.
They both call prim value.
And so
The difference
on
is
the
they're different
stack-
objects. They're distinction. So on the
Yep.
stack, so in our stack frame, when you send a message,
Right.
you've got your return address, your previous frame pointer, you have the method, that compile method for the send, and you have your heap environment pointer, and then your temps above that.
Okay,
So when we send value marked, the slot above the saved frame pointer is going to be a pointer to the compiled method value marked instead of the compiled method value. So it's a distinction.
and not the block that's being wrapped.
And not the block that's being wrapped.
So what about nested?
Nested ensure? Or there'd be multiple value marked on the frame or on the stack. So you'd be processing frames. You'd hit a value marked. You know that the next frame down, the next frame that you're going to process, is an ensure or if curtailed. You need to evaluate the argument to that frame. Here, let me
Is that the reason for having that intermediate synthesized frame that you showed us on the previous slide?
Yes.
So
It's funny, because
on this.
Yeah, that one. Yeah, the end.
So when we are in
In terms of a block, the previous frame from that is the reentry frame.
oops, sorry. So I'll make a quick frame.
But while I was speaking 5 seconds ago, I forgot the word reentry frame, so I called it previous.
Okay, so we have an ensure.
Like next from the top.
Right here will be a frame that has value marked. And then here we'll have the receiver. But the receiver block activated. So as I come down the stack, I hit the receiver block. It's not a frame I care about. I hit value marked. I know that the next frame is ensure or if curtailed. That means I have to process that frame.
So in other words, it's treating that as a special selector, like
Yeah.
in most small talks, Viran plus times repeat for balls,
It's
in a way. It means that generally you shouldn't go and implement value mark in any other random.
Oh yeah,
Correct.
yeah. You do not want to
It
read.
has a distinction. Yeah. It's like, don't you ever send it from anywhere else.
You shouldn't send this.
How about
Ensure or curtailed.
You shouldn't send this specific implementation of value marked from anywhere else. This specific implementation of value marked is known to the VM, and as I'm processing stacks, the primitive that does is is value marked. That knows if that method in that slot is the one that we defined as our marker.
So you can have another method that implements value marked.
Yes.
But as long as it's different.
We don't look at the selector, we look at the actual distinction, the compiled method.
Oh, okay.
Yep.
Just out of curiosity. Sorry.
So just so, if you answer this question,
Okay.
I will just trust you for the purpose of understanding what's going on.
Okay.
You've got a block that's wrapped.
So
And inside
this block?
Yes.
So we wrap this
Inside
block.
there,
Yes.
there's another one. Another ensure.
Inside of this block, there is no ensure.
There
We've
can't be.
there could be.
Okay, if there is, and in the execution of the inner block, you generate an exception that is handled by the outermost ensure.
Okay.
It seems like it would have to be able to know to skip over one of those marked frames.
Okay, and we'll get to that.
Okay, good.
Yes. Yes. Yep. And that's what I thought you were thinking about, but I wasn't sure. Okay.
So,
Okay. Was there a question?
it was
Okay.
a comment. I don't know if you noticed, but these later versions of Faro
Yes.
use that primitive that is unimplemented and then they check for send the primitive that fails.
Yeah.
Okay.
Is that
I'm not that.
no, not that.
Okay, so now we're walking down the stack, and we find a value marked. We know that we need to process this frame. We know that we need to send value to this block. And so John's here. He grabs the previous context, and he sends value to the first argument. That's how we activate our block arguments for ensure and if curtailed.
Which means now I'm somewhere way up higher on the stack.
Yeah, so we're processing on the same stack that we're walking. And so our non-local ret is actually a message send. Initially, we had it as an opcode for runtime. With doing block returns this way, that means that we're actually target agnostic. So our native runtime and our threaded runtime use the same C code. And there's a little bit of magic we do in assuming that the primitive is going to return in a specific way. But we're agnostic that way. So now John's at the top of the stack, and he does a block return. Now he knows how the block magic works. And so John's like, we need exceptions. I'm like, I have no idea how to do that, but let's try. So I start thinking, and I'm like, doing them in the VM seems like a bad idea, because doing ensure and if curtailed in the VM got really messy. So how do I do it in Smalltalk and have it work? And so I start thinking, with the ANSI spec, you have to jump around a lot, and you have to, try a new block for the retry block, or maybe you're evaluating default action, so you actually have to go back to the signaler exception context. So you have to jump around a lot, and the handler environment changes as you do that. So it wasn't clear to me yet. And so after a day or two, John tells me, take a look at BSE. And so I had just implemented blocks and ensure and if curtailed. And so it was like, oh, that's how we get those jumps. So this probably isn't exactly how it happened, but this is how I'd like to remember it happening. Trying to conform to ANSI Smalltalk. So undo, we can handle it just like VSE does. We can have an exception handler and have it process the exception. We can put it on the process object. As we're going up and down the stack, we can use ensure to make sure it's the proper handler. And ensure will remove it from that when we return from this undo. What about signal? We have to worry about resignal as and a couple of other things that VSE doesn't. Before ANSI Smalltalk. VSE was built before ANSI Smalltalk. So I added this exception processor. Let me open up. So there's non-local return. Ignore that for a moment. So when we do a signal, I'll zoom in. If we're already active, let's throw an exception. Otherwise, let's have an exception processor process us. And the reason we need this, so if we go here, we have to worry about resignal as and default actions. And so we have two classes that'll do this for us. We have an exception, that's wrong, resignal as token. And what this does is just tells the exception processor to actually signal me. So if we go back to exception processor, we'll set a default action block so we can return here in case of a default action, or if we need to resignal as a different exception, or we need to resume, we can come back to this point. And then we have the exception handle. So the other thing that can happen is default action. And so do default action, we'll tell the exception processor, but because we have these ensures here, we can jump back to this context, and all the exception handling, the exception handlers, because of the ensures, are restored. So now we're back to the signaling context. And wrong side.
Real quick, Question.
Yep.
Is there a part in this later in the presentation today about the interaction of FFI with the stack design?
No. We haven't really considered
There is
FFI
no
yet.
FFI, but any external calls will not be on the stack.
Yes.
Our Modtalk stack is never confused with the C stack.
And the way that you're setting up the C stack as far as FFI involvement permits things like string function stack guard
Well,
mechanisms.
as soon as we're done designing it, which is I think is after your next trip to Marquette.
Fair enough.
Yeah, we have not designed FFI yet.
The future is like
It is the future, but what we have found to be very useful in our design is our Modtalk stack is our Modtalk stack, our C stack is our C stack. Once we start executing the Modtalk program, the C stack does not move.
right.
And so our base pointer is EBX, or RBX, not RBP. On native, our instruction pointer is the instruction RIP. On our interpreter, it's a different register. And so what we do is we just do not confuse our Modtalk registers, our Modtalk stack with the C stack. And one of the hard things we had, and a lot of subtle bugs appeared when we didn't, especially with the native code, when we didn't maintain that invariant of the C stack does not change once we get into Modtalk code. Right. So for example, if I'm in native code and I do a call to a method, that will push the return address on the C stack, but the standard prologue will pop that return address and cache it on the Modtalk stack, so I can later return from that Modtalk method whenever someone decides to return to that PC. So we're doing all our non-local control stuff, and as we're traversing up and down the Modtalk stack, but when I actually restore RIP, it will be from something here that I push onto the C stack, and then I can just do a return. And that will take me to the right place.
Mm-hmm.
Right, so our C stack, once we call into Modtalk code running, does not grow, unless there are interrupts in red zone activity that we never see.
Mm-hmm.
And all of our Modtalk code is executing on the Modtalk stack, so when Kurt's doing all his magic of having smalltalk code walking up and down the Modtalk stack and adding new frames up here as ensure blocks execute, and then executing back here on return from that block value, and that all works native, interpreted, no changes.
Because that's your universe.
It's our universe, it's our stack, it's not C stack. Should we have external things where we're wrapping and handling it, C interrupts, we'll have to design some mechanism for translating and extending them into our universe, but we're not confusing the C host domain with the Modtalk interpreter domain temporally or physically, or, yeah, it's those time problems. Voters understand this.
You said that when you're running Modtalk, you really said that your stack pointer is RBX.
Our frame pointer. Our frame pointer is RBX, not RBP.
And are you using RSP? You're leaving RSP alone.
That's C's business.
There's 5 registers on
On
Exodus.
64-bit, there's enough free saved registers that we can map the Modtalk register set into those registers. So why worry?
Right.
And yes, I don't have a one instruction push, but it all's in the pipeline anyway.
Do you ever have to spill?
Uh,
Or because your execution environment is just defined registers, then you don't even
We still-
ever need to spill?
Kurt spills RNA all the time.
Yeah.
Oh my gosh. I don't know how many times I'm trying to walk through code and say, can we spilling the R and the A register again? So he's working on optimizing now. Hopefully, leaf methods won't have to spill.
Okay,
Right,
right.
but if you
then
are-
where
if you-
do you spill? Do you spill on the C stack or on your
Spill on the Modtalk stack.
Yes. Always the Modtalk stack.
Right. And because that's context, we'll need Modtalk. And again, that will be invariantly true for whatever runtime model you're using, native, interpreted, byte interpreted, whatever kind of runtime you have. You will always have spilled A and R onto the Modtalk stack because they're Modtalk universe.
So, just out of curiosity, with regards to exceptions, is it possible to run a Modtalk expression in a workspace?
What we could do is we could put an expression in a program and compile it and run it.
Okay.
We don't yet have workspaces, though.
I'm not sure I understand the question. Run a mod.
He has an exception expression he wants to test to see if he can break it.
Rather, an expression that broke other exception systems.
Let's try it. Do you have that program that compiles?
That it has something to do with that.
Probably, but I'm not sure where it is right now. Some of my code is currently broken.
We should use my machine.
Presentation
Okay.
during the break.
Do you want to do it during the
Why
break?
don't we take a break now?
Yeah,
And
yeah.
coming back, we'll do an experiment.
Okay.
We'll see if Anders can break Modtalk.
Whatever, it's just a known issue.
Yeah.
But it's a very long-standing issue, and so my concern is, well, it could be.
Wait, you've got to look at my last slide first.
Oh.
I spent a lot of time on this slide. And this is Wizard John. They don't want me to say magic anymore, so I'm running away from them and doing all the magic.
A rusty wand with a star on it.
And this is how we deal with not executing ensure blocks twice. So this red code has changed from before. So when I grab the first argument, I store a null block there that does nothing, and then I evaluate it. And if we hit the bottom of the stack, I'll throw an exception.
I complained because it was more than 5 lines of code.
If it were by lines of code, how much complaining I would have to do?
Cool.
Don't take my lack of response as being significant.
All right. I just love it when Pete star for cycles. It happens so early. Challenge from the audience. Can the Modtalk exception handler handle the torture test from Andres?
No.
And there's been some talk about this, so I want to show you how to very, 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 very carefully use the code that I gave you so that it doesn't blow up in your face and leave shrapnel in your eyeballs or something like that, because this is very much experimental test pilot, flammable rocket fuel kind of
Dude,
code.
DM engineers, right?
Yeah. You've seen my code before. Who am I pretending to? Let me get my font a little bigger here. Settings, appearance, medium.
DM engineers, right?
Okay. So, first of all, there's these two expressions in this workspace. Repository browser open will open this project. It's a repository browser. There's a repository on there with some pre-packed projects. By default, it hasn't actually cloned a copy of that repository yet. So when you selected it, an open will actually cause us to clone it. Now notice very carefully the title bar says choose the parent of the working directory. So I want this to go into my contents directory, so it'll choose contents. Right? And it will clone into there. So if I say, okay, I see we've provided you with is the ANSI tester project, the Delta Blue project, the Nano project, and the Simple project. Right? Other things to note. Let's open Nano and...
So I opened the zip file that it provided.
You open the zip file,
Inside the app bundle, and I take it, show the package contents.
double-click the app bundle.
Just fire it up.
Just fire it up.
You should change that so if there's like 8 or 10 really complicated command lines in order to get started.
Oh, Pete. There's so many ways. Pete, we have many hidden ways where Git will fail and not let you know because I'm not handling that in the GUI.
If it feels like the environment froze, it probably didn't.
Yeah. Because it prompts you for passwords occasionally.
Yeah, if Git prompts you for a password, and if you try to actually create a project of your own, So right now I'm hand building the project in the Git repository, checking it in, and building the URL, and then it checks out just fine. So we've got a lot of tool work to do.
Okay.
It wasn't a top priority.
Yeah.
Again, when you selected that, open, it's going to be the same story. It is possible, I don't know why it's not storing annotations. The normal way we do it is, so I have to say contents again. This rapidly got annoying to me. So I set it up that it gets the Git email for the current user. And I'm using the global one, and I probably shouldn't use the global one.
No, so just by way of clarification, the 8-complete command line thing was intended purely as a joke, implying that you obviously would not do that intentionally. It was just a joke.
How long have we known each other, Pete?
It seems like for about 1,024 years.
And a couple months.
In 2 months.
Yeah. Okay. Yeah. So that opens up a project browser. You can choose them. I think in the code that I snapshotted, not all of the projects seem to be working on the threaded interpreter. And in general, there's a debug, which is our threaded interpreter runtime.
It should all work with Delta Blue.
And native. I think on mine it works both, but on some Linuxes, I think the threaded was having issues on Delta Blue.
Yeah.
Compiling. New compile, don't even think new compile is a good choice.
It's a good choice if you want.
Bad choice. Bad choice. Okay. So when Kurt was experimenting to getting his process scheduler to run, and he wrote a bytecode interpreter in Smalltalk, new compile builds that, and we made a lot of wonderful discoveries about refactoring that way. But you're going to choose plain old compile. It will run, and it will show you this. The first time you...
Do you want me to sit next to you?
Yeah, Josh, go sit beside him and pair.
Okay, I'll pair with you.
Oops, that's not what I wanted to do. Ah, where did my...
Okay. Hey, are you supposed to select
I don't know.
Choose content.
Yeah.
I think you use a project.
You don't have to.
You don't. You have to open projects. So select projects, right-click over projects, and open.
And then you can go ahead and close the profile. That's for us, not for you. And
You don't have to go to contents.
So did you
Oh, yeah, to contents, yes. Yes.
you will just go, if you open up a journal, if you open up a journal, go to
Yep.
go to new journal session.
Yes.
And then
It didn't go me as tester.
yeah.
It won't until he opens it.
Where are you right now?
Two-finger click open.
Let's see.
So the one on the left
Go
hand, that's what
into-
we're doing. That's what we're doing.
Select projects in the left pane, and all the projects should appear in the right pane.
That's not what's happening. We're
Oh, he's
selecting
got projects in the
So
right.
what you did is
That's weird.
How did you get projects in the right pane?
Check them.
So what would happen is we
These first.
yes, you created the people. So this is a repository containing all the project specifications.
Okay.
So if you go ahead and ls
It's
project
projects.
directory,
That's weird.
That's weird. We'll figure that out later, and you'll just have to watch.
so
Okay.
you don't have to really you can cat.
So I'm going to close this. I'm going to open up ANSI Tester because I know it has SUnit in it. Contents.
So what a project specification looks like, it has a name, and then it has a bunch of repositories.
It's cloning a bunch of repositories, and there we go.
That corresponds to the program.
And actually, I will set this on native.
And these are all of the build targets. If you go back into Pharaoh,
Okay, so Andres, we could do one of two things.
the two build
We could just add an expression in this workspace, but I'd rather add it as a ANSI Tester test case. So ANSI Smalltalk test. Shall we create an exceptions test case? Where's that blocks test? Oh, it looks like blocks test is where it goes.
Okay.
There's different compiles. It's our build target.
So you want me to run this?
Here, let me just make this font bigger because that's just really hard for everyone else to see.
So it doesn't matter which one.
Okay, so yeah, and to see subclasses, just
You click compile, and you use that.
so
compile. So
probably here. There's some. Okay, there's
Oh
a.
yeah.
Okay, so
Go and CD into your nano. So this is a nano project. So we have source code for our Nano project.
I'm interested because
that contains our Nano project.
we had doing exceptions and just it was complicated.
Yes.
And I just wanted to see if his
It's really tiny. Yeah.
if his torture test how I would react to that.
Directory. This is where it compiles.
Yeah, well, it's interesting because these guys were first exposed to closures a year ago.
So you can go ahead and make the project.
This is non-trivial.
Yeah.
And then you can run, if compiled, we're doing actually tool called Nano. So if you run Nano, it runs. And
I guess we don't need the camera for this.
No, it's okay. It's okay.
No?
It's fine.
Okay.
I'll do. Let's capture and then deal with that later.
Okay. Oh yeah, you can edit it out, right?
Keep going.
Yeah.
Yeah.
We don't have 0 divide yet. That's working.
We don't have zero
these
divide.
are the, this is like the, what we have, this is the,
Included here is my test error,
representation that we're
test
compiling to.
notification. You can see them in that global scope there, or that scope there.
Okay. Yeah.
Presumably, do you have a test error?
So if we want to take a look.
Oh yeah, my test error.
The actual.
Do you need a notification or an error?
No, that's fine.
If you want to take a look at the actual program code, we can go to nano_code.c to look at the code that's generated.
Aren't we supposed to point to like an empty volume or something like that?
So
No.
we compiled for threaded interpreter. So each one of these are like opcodes.
We'll look at it after.
So we push the frame pointer, move the stack pointer to the frame pointer, push X, push nil, allocate an environment. So so I mean that's the entire code sequence basically. It's not big because you're not doing a whole lot. Small 242. We're loading that.
Close code.
So So that's the code, and what else?
But this is not
Signal?
Signal.
Oh, okay. But this is not exactly where I want. So finally. No. Come on.
MIT license, yeah.
The X over there?
We learned the 32 from the vendor wars.
So I'm trying to reconstruct it from memory.
What's it called? What's going on? It's because Git is not.
Do you have a test case that does it?
Oh,
No. This is the test case that they did for Arrow.
Ah.
Yes.
Yeah.
Did you mention we assume you have
throw the
Git set up?
exception as this handler.
Right. I
okay.
that.
And
That's what I was thinking.
And then
So what happens is
We saw, right?
you keep commands occasionally, and then
I never expected
Oh.
code.
If they don't work, for example, if this happens, why doesn't it work?
So on his machine, you have to agree to the license.
Yep.
And we're not checking exit codes.
Yeah. So what happens is if you do a git status right now.
Git status?
Yep. Git.
Just
What?
Zero senders.
Oh yeah. Just remove it. Okay. Not all of our tools are done, Mr. Butler.
No, it's a browser. It's a zero sender.
My little friend. We have been refactoring, and we just added our directive table. Okay, so to run this test, we need to add. We're not reflectively getting it, so we have to grab this selector, go to the class side, go here, and add it to the test method selectors.
We need to do git clean. Sorry, your program's not clean. And now if you do another git
Okay.
status,
Now I go up
Now
here.
that's one.
You're on
Yes.
master branch.
We're on the native. I'm going to go here,
So if you do another
and and it is going to run the zero argument block closure test case. So I will compile this,
it'll just compile it to default.
Which is the password for that.
and that's done. And now I go someplace to make that small and make that small. I get a shell.
Right,
Okay,
yeah.
new
You can
shell.
switch it to GDB and it'll work fine.
Okay, so here I CD to desktop, there are one-click app, CD contents, and it made my project working directory here,
So these are
right? And we compiled for native, so I do a make here, /nc tester, and we were looking for zero argument test case, test nested handler lookup. Yeah, that passes. Woohoo! One more test passes.
What is this test? What is the test that he
Okay, so the test that he just added
I don't think so. Are you going to?
is that was in the
Type in your password. So
block test. Oh, and so other things. So some of the things we do have kind of working are Andres just changed this package blocks test. So the star means that it has Git modifications or has been added. So it's not saved. It's not committed to the local repository yet. Is this going to work, Josh?
What?
If I stage it?
Oh gosh, I have no idea. Probably not.
Oh, not anymore. Yeah. So at one point we could stage that it turns to an angle and then you commit and it's clean again.
dash.
Okay.
Or whatever it is.
Okay. So the one that was just added was test nested handler lookup. Test nested handler lookup.
Okay.
Well,
What's that?
so when you're handling an exception, that handler needs to be pulled off like the handler chain.
So if
Any
you
other handlers
Yeah.
behind it need to be activated. So when you go into this and run this in barrel,
All of the handlers need to be activated. Okay. So if you're
actually this isn't a test.
Oh.
it's this. Okay.
Andres,
Kurt is going to fix your code, Andres, because you made it.
it's
this. There we
you're
go.
in this test error. So this is actually a throw out my test error.
That's moderately annoying.
That's what it is.
Okay, so why don't you explain this to us up on the board?
It's actually related to
Yeah, you.
Is it like that, really?
It was like that because
So if you have a git command and
the thing was in the
key,
second
you can have
handler.
like an RSA
So there's something higher on the stack.
or you just have a
Oh, right.
button
You
to get
you raise it here, but it's
exceptions. If Pharaoh this handler fires,
It should be this handler like that. When we execute the git command, the subprocess, it will use standard.
Yeah, that does look like a more
And
challenging
the terminal
test.
would be like, hey, would
Wait
you
a
like to
minute.
enter your password?
So you
And then
raise
Pharaoh would
this one, so you skip this one because it doesn't matter. And while you're doing this,
So
you see now,
if we fix that, we can probably fix it.
and what you want to see actually is
You want
See, yes, and the interesting thing is that is on the stack.
it's lower. It's
so that's not fair. Because how is this going? How is this one going to run?
because this test notification is how here. We have
Oh, right. Yes. Okay.
Okay, so we need to recompile and rerun, right?
Yeah.
Okay, so let's.
I can reset it.
Oh, okay.
There's a command that I can
Okay.
Honestly, what you want is to execute a command that's basically a no-op that you can just get the result from. If the result's okay, then when that whole thing
Woohoo! All the tests passed.
you can do it. If not, you're out of that.
So,
Whatever.
if you
Okay, yeah, so.
So, you can't
Woohoo! We do things right!
You don't go ahead and close this browser for record.
Yeah, that is the thing. I mean, that was like a few months ago.
There would be a standard kit, and then you have a sort of command option for the outer script that says, I don't care, just ignore that.
yeah, I'm sure there's kind of a
Having nested prompts for passwords
This is
is
a little bit more complicated project.
Trey and I.
It has a program.
I didn't know you spoke French.
So we've moved on. Which has Did you guys get it? Yeah.
Yes.
So the issue is,
All right, so do we want to just go to like breaking up in little groups and work on stuff?
yeah.
Yeah.
That's why I was saying.
Well, Zisha?
So the issue is when you first execute git commands,
Yeah.
They prompt you for license to read.
Yeah.
So
We
I think
are
we
not
can.
graceful.
Did everyone get a copy?
It seems like how on the option.
That's a trivial thing.
What?
Source code?
Oh, you only have
I'll get it.
Yeah.
crazy one.
Well, and anytime, I mean, it's certainly the case, view, bonus, whatever. I think we're more than willing to give you a and then you can just go to our main
That method's not in this project, but in another subsystem reports the class and adds that method.
You can care what and the issue with that, right?
So in subsystem,
oh, right. Oh, look. When you're reading some other point or some other strings, you get that information.
if you're in subsystem A, and have a single object act differently depending on what subsystem it's in. What subsystem the code that's executing, which messages
So this one, for instance, what is the current
if it's visible on that object in that namespace.
Void star. That points to the
by
last object.
by running into with this is it breaks things like the template method header. So it's not useful for an object to activate that behavior.
And along with
you can't subclass and redefine some method.
Yeah.
So you're kind of SOL.
Right. But the interesting thing is, if you have undefined behavior in one subsystem, you import the class, and then you
But they're both
import.
singular.
So the scope that's built for any methods that are built in this subsystem
pointer casting
start with the and the outer scope of those methods is the class itself, so it won't be able to see the method that you add. So then when we extend behavior to the class, should we be adding that behavior to the